So right now I'm going to draw the series circuit. Okay, so LED, this is a diode first off. The little triangle tells you the direction of flow. It's going to go in a clockwise loop. All right. But then in order to specify that's a light emitting diode, you have the little squiggly line with the arrow coming out of it. Okay, so let's assume that our power source is going to be 9 volts here. 9 volts. This is series. What is the voltage between point A and B? Yeah, what's the voltage between point A and B?
1/3 of 9 volts.
Yeah, that's right. Do you see where you got that? Why do we get 1/3?
Because it all has to add up to 9 volts.
Well, actually, it's going to be even less. But because we have another device right here, which is this resistor. But let's just assume let's just assume that the resistor's not there, okay? So then, like, theoretically, it's going to be 9 volts divided by 3 devices, all right, in series. That will equal 3.3 volts, okay? All right, now for these LEDs to turn on, you need a minimum threshold of 2.2 volts.
It's 3 volts, not 3.2.
Oh, I'm sorry, you're right. I was thinking 10 somehow. Yes, thank you. It is 3 volts, okay? So 2.2 volts, minimum threshold LEDs turn on, okay? Which means if you're under 2.2 volts, it's not going to turn on. Now, without the resistor in there, are we above that minimum threshold?
6.6.
Huh?
6.6. If it's 2.2 times 3 would be 6.6
Yeah.
volts.
So
That
right
would
now,
free them.
between each LED, we have 3 volts, right? And then our threshold is 2.2. So will the LEDs turn on at the moment?
Yes.
Okay, good. All right. Now this resistor that we choose, it's also in series, right? So really, the voltage is going to be, components, it's going to be resistor 1 plus the voltage of, let me give these some letters here. I'm going to give this letter A, B, C, D. Okay, so voltage total equals, it's going to be resistor, it's going to be voltage of A plus voltage of B plus voltage of C plus voltage of D. Does that make sense? Okay, it's going to be the sum of all of them. All right, our total voltage we know is going to be 9 volts, right? Voltage of A, I don't know. Oh, we don't know, but because that's going to depend on the resistor. So I'm just going to leave that a variable VA. Okay, VB, C, and D are all going to be the same because they're all the same LEDs. Does that make sense? Yeah,
We're looking at the blue A, B, C, and D, not the red A, B, C.
Yeah, I'm so sorry. I should use numbers here.
Do 1, 2, 4.
Okay, I should use 1, 2, 3, 4, 5. Right? Okay. Yeah, so it's going to be the blue. Okay, well now there's only one. Okay, so the LEDs are the same. Does that make sense? Yeah, the LEDs are the same. And let's just say we want to target. We're going to give it a target voltage. Let's target LED. What do we want it to target? It needs to be at least 2.2. Let's go a little more just to be safe. Yes?
Actually, after threshold,
Yeah.
it keeps at 2.2.
Oh, it
It
does.
doesn't change.
Okay, fine.
So,
So
wait,
it is
2.2.
2.2. Okay, I'm sorry. So then, thank you. So then our voltage of LED, we need to set that to 2.2, right? Okay, so then that's going to be 2.2 plus 2.2 plus 2.2. Okay, and if I want to be more picky, really to be more accurate, we want to put the units in here. Okay, so what's 2.2 plus 2.2 plus 2.2?
6.6.
Okay, VA plus 6.6 volts. Okay, VA is going to equal what? 9 minus 6.6. 2.4 volts. Okay, we have 2.4 volts. Now current. Okay, current when a resistor is on is 20 milliamps. 20 milliamps. Okay. What's the rules when it comes to series circuits? What's the current between 0.12, 23, 34, 45?
It's the same.
It's the same throughout. Okay, so if this thing is a 20 milliamp, it's 20 milliamp across every single component. Okay. What is the rule? What is the law that I was showing earlier that relates voltage, current, and resistance? So I'm going to say I of 1 to 2 equals I of 2 to 3, which equals I. Remember, I stands for current. 4 to 5. Okay, that all equals, let me just move this down a little bit. That all equals 20 milliamps, which is the same as how many amps?
0.02.
Huh? Okay.
0.002 amps.
That's right. So I'll just show you how we got there. There's 1,000 milliamp in 1 amp. So what's 20 divided by 1,000? Did I do that right? Right?
Yeah.
Okay. So it's 0.02 amps.
Should have 3.
Huh?
Should have 2 after the decimal. 2 zeros after the decimal. If you're dividing by 1,000.
Oh, you're trying to do sig figs? Like you mean like this?
No. There should be a 2 in front of, a 0 in front of the 2. If you got 3
A 0 in front of.
zeros, you have to have 3 zeros on that side of the decimal. No. 3.
No.
No, 3.
This is 20 divided by 1,000.
1,000.
20 divided by 1,000. Yeah, that's right. Yeah. Because you're thinking 2 divided by 1,000, right? It's 20 divided by 1,000. Okay, sorry. I thought you meant sig figs, which we're not going to worry about right now. Significant figures. Okay, so I'm converting it to amps because when we do something like, remember that law? I don't want to say it because I want you to figure it out. Ohm's law, yeah. V equals IR. You can do things with different scale of units, but then you have to also keep track of that. Versus if you keep everything at the baseline, like times 1, right, voltage, it's not millivolts, it's not kilovolts or anything like that, then you can just keep using the same non-scaled up version. Okay, so we have V equals IR, Ohm's law. So what's our V across 0.1 and 5? Sorry, it's a little off, isn't it? Okay. What's our V across 0.1 and 5?
9 volts.
Is it? We were just talking about that. Look, we just calculated this out. It's not 9 volts because remember we have a series circuit, so everything has to add up. So across component A, which is our resistor, we calculated right here. You see it? 2.4 volts. So does everyone get that? Right? We calculated previously. We're talking right now. This is the component of interest that we're talking about in this equation right here. This is the one that we're worried about. So if it was here, yeah, it could be 9 volt. We're worried right now about that. So it's going to be 2.4 volts. The current, what's the current?
20 milliamps.
Yeah, sorry, this kind of got squished, didn't it? Oh, it's right here. Let me just draw a line just so we can distinguish. We were doing voltage earlier, and now we are doing current. Okay, and now we're doing resistance once again. So draw one more line here. Okay, we're doing resistance. Okay, so I is going to be 20 milliamps, which is 0.02 amps, and then R. Now we want to find the resistor. This will tell you what resistor you need. Okay, what's 2.4 divided by 0.02? It should be 560, right? 2.4 divided by 0.2. Oh wait, 120. Sorry, I did the other way around. 120. What's the unit? Does anyone remember the unit for resistance?
Ohms.
Yeah, which is written like this if you look at your multimeter.
Omega.
Okay, now you can either keep trying the different resistors that you have in the box, or you could look up resistor color code. Okay, let's see what we got here. So I want to go the other way around. Here, let me give it a value, 120. Okay, we want a red brown. So if we look here at the box here, I don't know. It's a lot of searching. Brown, red, brown. Now, you may not find exactly what you want. So this is where it's important to understand the colors. If you look here, the very first one is the first number. So you see 120, we have the number 1. The second band is the second number. So 120, the second digit's 2. And then the third one's the multiplier. So what's 12? 1, 2, which is 12 times 10. 120. So what matters the most, really, because we have some variations, right? All these are theoretical values. So, like, in reality, the resistance might need to be a little lower or a little higher or anything like that. So, and we can play with the voltage ultimately here too. But what matters the most is actually this multiplier. What if we were the next number, which is brown, orange? That's 130 ohms. If you do the calculations again, it's not really going to change much, okay? So this will be fine. So really, if you found something with a brown, another color, and a brown, you're probably going to be okay. So if you look here, is there anything that's a brown? Some color, ideally we have red, but if not. So I have here a brown, black, brown. What is that? What is a brown, black, brown? Maybe this is probably going to be usable. What's brown? Okay, so that's 100. 100 ohms. Okay. So you could probably use this one. You find something else? I mean, there's a bunch of resistors in here. See if you can look on your board and tell what type of resistor you have. What we want to be careful of is if you choose a resistor that's too high. So let's say you went into the so really, if your third bar is anything higher than, I think red we can still work with. If it's by 100, so now it's 1,000, which is kind of high, but we could probably just crank up the voltage more, okay? But if you have orange, yellow, green, blue, anything like that, this thing probably is not going to light up. So can you check your resistors on your board and make sure, ideally it's a brown in the middle as a third band. You got something brown. Okay, that's good. That's a good sign. All right. Pink? That's not even an option.
Take your sunglasses off.
Something brown. Okay, that's what we're.
Some are all like,
Okay, then we should be fine. Now, okay, let's see if this same resistor applies when we do series. All right, so this is our target resistor. You see that now? You see this is our target resistor? Okay, but again, I'm sorry.
How do you know which way to go? This way or this way?
yeah, I was going to ask that. Yeah.
Oh, it's going to be clustered. You see, okay, there's going to be one other color on the very end, and that's going to either be a gold or silver. Gold or silver band typically. Yeah, typically that's what you're going to see. That's a tolerance, meaning if you see a gold, it's going to be, in this case, 1K plus or minus 5%.
So gold or silver you get,
Yes. So that's how you know that is the tolerance end, and you should read the other way around. Yeah.
So how do you the gold is at the end?
For the resistance.
The wattage of the resistor, well, watt depends on the voltage and the current, right? Because power, P equals IV. So,
These are usually a quarter watts little resistors.
Mhm.
somewhere around.
Yeah.
So,
How do you?
bigger resistor, more wattage?
It should be bigger resistor can handle more current, I believe, which I guess is more wattage in a way, because that's current is one of the things. I don't know how you can tell. I don't know if it's something you could tell by equations. I think it's something you have to look at the data sheet. Is that right, John? Yeah, I don't think an equation is going to tell you, because these are like our requirements, but this is like a hardware, and then you're looking at the hardware and trying to figure out what it can handle. Yeah, John, what were you going to say?
I think the whole thing is color is color. Everything different register value, but still color. Yeah.
Okay. All right. So can everyone see on the resistor the which direction to read? It might be easiest to see the tolerance level, which is generally a gold or silver. If you see that, let me see that little resistor ahead up here.
I think I understand it. This is gonna be tricky. Look at this is yellow, white, black,
That's
and
gold.
then gold
That's gold. Yeah.
at the end.
Actually,
this is starting
let me
with yellow,
see.
right?
That's orange.
But that's the start. Though.
Yes, that's
Yeah,
a
so
start.
that can
Orange,
confuse people, right?
orange, white, black, and gold.
Yeah.
Yeah, that is. I mean, you kind of have to look at either end, and you have to know.
Right.
Okay, that's a gold.
Well, now that you told me that gold or silver is the
Yeah.
end, I just
Now you can also take a multimeter to it, right? And you can verify.
yes.
That is the easiest way.
Yeah, that's the easiest way than like straining your eyes.
Also straight.
But if you have a bunch of resistors in a box like what we have here, that also kind of sucks to take a multimeter. If you're very quick, you can just like look at the third row and you can figure what order magnitude is. You're looking for brown, black, and if you know the next one is red, then it's then by 100 and then 1,000, right? So, okay, so that's what those colors mean. Now let's measure out the next one for the parallel circuit. Let's see if it's still the same case. So if I have a parallel circuit like right here, okay, I'm going to draw this again. All right. So now I'm going to label these components A, B, C, D in blue. Okay, A, B, C, D in blue. A, B, C, D in blue. And then I'm going to put points 1, 2, let me see. Yeah, I'll just do this. 5, 6, 7, 8, 9. Okay, some of these basically are the same, but just for visualization. Okay, so what we have here is a parallel circuit. So what does that mean? What's the voltage when it comes to voltage A? Okay, so this is the 9-volt battery. Let's just go there again. 9-volt battery. Voltage A, voltage B, voltage C. You have two options. It's either the summation or they're the same. They're the same, okay? In parallel, voltage of the system, which is 9 volts. 9 volts. 9 volts is the same across every component. Oh, shoot. It's not going to be 9 volts, though. Let me just do this for now. Imagine the resistor D is not there. Resistor D is not there. Then it equals 9 volts. But resistor D is there. And look at the relationship between resistor A and the power. It's in series, right? You see, this is in series with each other. It's one after another, meaning the actual voltage you get out is not 9 volts. It's going to be less, okay, because of the way that's set up right now. I'm thinking...
There is not 9 volt, there is a 2.2.
Eh?
That's gonna be 2.2.
What is?
The VA, VB, VC
Yeah.
gonna be a 2.4.
Should I put the resistor here, John? What do you think? Instead of at the beginning? Because right now it's basically just having a lower voltage by having the resistors in series.
Yep, you can do that separate, you can do that like
Because I don't see a point in having this resistor since it's just in the beginning. It's like, it's just might as well put an 8-volt battery instead of a 9-volt battery by having it in the beginning,
yeah,
right?
that works.
I think we actually need to have the resistor in each. To me, I think, right? I don't know. Sorry, I'm second guessing myself now. Let me just draw it that way. More soldering practice for you, anyways.
Oh, yeah. Good
Uh,
idea.
All right. All right, then.
Thanks, John.
No. It's just my idea here. Okay, let me do. I'm gonna do RA and DA. Okay, so for D for dial, RB, D, DB, RC, DC. Okay. And my OCD making me want to redo this in the middle. Okay, all right. Okay, anyways. Okay, let me redo some of these numbers. So we have 1, 2, 3, 4. Oh, shoot. And do 1, 2, 3, 4, 5, 6, 7, 8. Okay. All right, so the voltage across each of these, I'm going to just call this entire system, instead of A, B, C, it's going to be between 1 to 2, 3 to 4, 3 to 4, and 5 to 6. Those are all going to equal 9 volts. Okay, that's a more accurate way, okay? Okay, each branch is going to equal the same as, they're going to be the same, each of them, okay? What about the current across 1 and 2? One to 2. Okay, I total. Okay, current is a summation now. So previously in series, current was the same. Now current is a summation. We know that the current we need across this diode is what, if you remember? 0.02 amps. So we need the current. Now this thing is a mini series. Do you see this? This is a mini series circuit. You see right here? You see it? Yeah, okay. So in series, our current is the same across. So that means right here, we need 0.02 amps. 0.02 amps and 0.02 amps. So what is our I total then? 0.06. Okay. Good. Okay, so because our current is going to be the same, V equals IR, remember this? Ohm's law? Yep, Ohm's law. The voltage is going to be, okay, let me be more specific here. V1 to 2 equals I R 1 to 2, and this is going to be RA, yeah? Because we only have the resistor there. Okay, so what's V1 to 2? We did it previously up here. Do you see that? 9 volts. 9 volts. The I is what? We did it right here. 0.02 amps. And then the R is literally going to be the same thing, right? Yeah, we did the same thing. Oh, no. It's a little different. Oh, it's a little different. What's 9 divided by 0.02? 450. Okay, that's our resistor. What's the color? I'm going to do 4, 5, and 10. 450, right? So yellow, green, brown. All right, we're still dealing with the brown, yeah?
Is there are 3 resistors at 450?
Yes, all three are the same. Because if you look back at this, basically, I just chose the 1 to 2 right here. I chose 1 to 2, but I could have done the same thing for 3 to 4. It's the same equation. And then 5 to 6 would be the same thing. Right.
Actually, you have to think about the LED voltage drop, 2.2.
Oh, yeah.
Yeah. So each register is voltage is 9.
Oh,
minus
right, for the
2.2,
voltage,
and
yeah.
then calculate. Yeah.
Sorry to make things even more complicated. Yeah. No, this is right. That's right. Okay. So the voltage is actually, it's going to be the voltage of resistor A plus voltage of diode A. Does that make sense? Because this is again in series. This whole thing is in series. So the voltage of resistor A plus diode A. Okay, let me do this one over again. Sorry, make things a little confusing here. Okay, voltage of resistor A plus voltage of resistor DA equals voltage of 1 to 2, right? Do you see that? How many people do I still have? Am I losing people? Okay. I'll space it out a little bit more. Okay, I'll just complete this, and then maybe it'll make a little bit more sense when we keep doing more and more practice. Okay, right now, imagine this thing. This thing is its own circuit. Ignore everything else. What do you see here? What do you see here? Huh? What's that? It's a series. So what is the voltage in a series? Across, are the component voltages the same, or are they the summation?
The summation of the 2.
Yeah, they're the summation of the two. The current's the same. Okay, so we're calling that the total voltage 1-2. You see, I'm doing that right here. Voltage 1-2. That's what I'm calling it. So you can see I'm doing a summation of RA and DA. Okay, we know what's 1 to 2. We did that previously right here. It's 9 volts. And we know the voltage drop across the diode, the light emitting diode, is what? 2.2. So then what is the, we're left with finding VRA. So what's 9 minus 2.2? We did this previously. 6.8. Okay, last time we got something different because that's where, okay, that's it. Okay, now, really what I should be doing down here is I should be saying this is voltage of RA, current of RA, and resistance of A. Yeah, that's really what I should be saying here. Okay, let me remove all that stuff. Okay, so now we have current of RA, which we just got from here. This is going to go right there. That's 6.8 volts. Okay, now it's 6.8 divided by 340. Is that right? Does that look right? John? My sanity check here.
Yeah.
340. Okay, we need a orange, yellow, brown. Okay, third one is still brown. So if you have something else, it's probably going to still work.
Funny thing at the register, they don't have all the numbers actually, like the 330, but there's no 340.
Oh, really?
Actually, really sell.
Oh, really?
Yeah.
Okay.
Not many. It's a kind of a
Yeah.
steps. So around that.
Well, let's see. I'm going to search their catalog, and like John said, there's actually nothing. There's nothing in 340. So
Find the 330.
330. So that's where we might have to there you go. You can find a 330. So this is reality, right? Reality is we can't get 327, right? You're not going to get something like that. And also the tolerance doesn't really matter anyways, because even if we go back to our other one, what do we have? We had 340, right? Plus or minus 5. What's 5% of 340? 5% of 340 is Yeah, so like 3.4, 340 times 1.05. So this could have swung all the way up to 357, or it could have swung down to 323. Did I calculate that right? It's plus or minus 20 or 17. It's plus or minus 17. So meaning there's no point being super accurate with the resistor anyways because they have built-in tolerance. Okay, so your resistor for this is going to be 120 ohms. Your target resistor, okay, because as you can see in reality, we can't always get what we want. Your target resistor for the parallel is going to be 340. All right, so we'll find it accordingly. We'll take a break. All right, sorry, fry your brain a little bit. And then look here on the screen. This is our target model of what our solders should be. So I kind of just let you, bond and connect them however you want off the board. But really, in reality, all the bonding needs to happen on the board. And specifically, your joints need to be nice, clean, shiny, like Hershey Kisses, okay? Just like you see there. All right. Now, these are what we call PCB boards, printed circuit boards. So underneath or on top, you'll actually see the lines. There's multiple layers, just like an apartment building. There's multiple hallways and stuff like that. So you don't always see everything, but you will get to see it at least on the surface level. So what we are working with here is something more like this, the copper strip board. We don't have those multiple layers. Some of you might, though. So you either have two types. You either have the type which is orange on both sides. In that case, each hole is its own island. They are not connected to each other. Or you have this type, which is orange on one side and it's green on the other. If you look at the green on the back side, they are actually connected by the letters. Do you see A through W? A through W. Okay, those are your columns. Those columns are all connected underneath. So this is like a one-layer PCB board. So there's a channel underneath. Each of them are electrically connected. So if you touch the multimeter on anything from a specific, the same column, it will beep on the continuity mode. Okay, because they're all connected. Meaning, you don't need to bridge things if you connect things on the same column. All right. Now, this one, for example, is not connected, even though it's green. Green doesn't mean it's connected. It's just, in our case, these green ones are connected. Let me see if I can show. Okay, this is like what you would have to do. I don't like this because there's exposed wires. This is not as ideal. Okay, this is something more of what you would have to do if you have the board that's not connected. And actually, even these boards, occasionally you have to connect things, okay? So you see how they're not connecting things off the board, right? Things are on the board. That's how they're connected. Now, we have our little leads sticking out, and those are going to be there until you show it to me, and then we can snip it off, all right? Because if we need to make adjustments, it's a lot harder to make adjustments when your leads are cut. So we'll make sure that we adjust that beforehand, or before we cut it off. Okay, I forgot right here. 60-40 solder temperature is what?
700?
I'm not getting a good number. Oh, 700 F. Okay. Does this one change last time? Remember we were doing that whole whatever it's called, the thread locker thing. Remember last time we were changing it? So this number changed. Okay. All right, so I'm going to first desolder, because this particular example we need to remove something. So this is also a good demonstration. The solder sucker, do you still have it? All right. Can I actually demonstrate with this too? Is that okay? Okay. So there's two ways to remove solder from an existing component. We have a solder sucker right here, as the name implies, it's going to suck the solder out once it's molten. So it's spring loaded, and then this tip right here you place right against the part that you want to remove, and then you press this button here, and it's going to pop out, and it's going to suck it out here, and then you have to reload it again. And when you reload it, it's going to dispel any solder that is sucked out, and it's ready to go. So it has like a ballpoint tip, and you place that right against the molten solder, once you melt it, that is. Okay, so let me demonstrate here. I'm going to melt this.
What do you call that gun?
A solder sucker. So right here I am melting. You see? Okay. Right now the solder is actually the soldering iron is not really melting it very well, and that's because I need to tin it. Okay. We don't have flux and everything like that, so we're kind of just. The flux would help it. The flux would help it flow better, but we don't have all that stuff. So I'm gonna need to tin it first. We want it to be nice and shiny. Right now it's kind of dull. That's gonna help with adhesion and like just. All right. That's all the flux burning off. I'm just gonna go here, clean it off. Okay, we want it to be shinier. Don't breathe that stuff. Okay, it's a little bit of a shinier surface. Focus. Alright, it's a shinier surface. Okay, now that I have that, I can go in and I'm going to load this sucker. You see it's already loaded. Okay, you can see the little ballpoint piece sticking out. I'm going to melt. You see I melted it. It's molten. I place it right here. I suck it up. And then I dispel it. Alright, not much has come out. But I'll do it again. Okay, it's molten. Suck, dispel. Now this one actually got, physically the wires are crossed over, so I'm going to just split them out. Now unfortunately, if you look here, I've actually ruined the strip that holds them together. So this is the rail that keeps them all connected. There's a thin film on top. I've already ruined it. And that's because these things aren't really meant for you to like redo it. So that's okay. We'll just work on another area. But for now, let me just remove as much solder as I can off of this part. So that's the film. You see, that's the film that I'm pushing around. Alright. Okay, let me see if I can get the Alright, so that's this side. I need to get this other one. So same thing. I'm going to first see if I can first suck. I'm molten. Okay, not much. A little bit more. You see, I got some out. You see, this is stuck on the solder sucker. That's the extra solder that's come out. So I got some out. Okay, again, these are like physically bent over. We don't really ideally want to bend these wires over. They should all come out straight, and then you clip them. Yeah. So there you go. I can now free this part. I think I have too much solder still on this end. So let's use the solder sucker to try to get some of that out. Still has a little bit more. So toward the end, I'm just gonna grab it here. I'm gonna give it some tension. And then I'm just gonna solder it. And yeah, there you go, I release it. Okay. So I just show you that one. So we're not gonna be able to reuse like first and second row anymore. You see it's kind of ruined. So I'm gonna go down here. So I'm gonna continue doing the other ones, but let me just show you how to properly solder. So I'm gonna take this one. Now this has been clipped, so we can't really just rely on the short and the long. If you had a new one, you can rely on the short and the long leads to know which side is which. But if you look on the inside, do you see the shape? It has like a slot, and the slot is slanted. So we want to make sure, I forgot which one's positive or negative.
I think the right is, well, looking at it, I think it's the right is the anode, the positive.
The right is the anode,
Yeah.
which is the positive. Okay. So basically, it's like a battery if you put one in like a remote control or something like that. The positive of one battery needs to touch the negative of the other, okay? So what we need to do, if I have two diodes like this, if you look, it needs to be facing, the slot needs to be facing the same way. You see that? They're facing the same way. So we can't have this. This is not going to work because diodes need to flow in one direction. So either they face this way or they face this way, okay? And later on you can figure out which one's right by just changing the voltage. Okay, so I'm going to choose down here. Let me do B16. Okay, B16. I'm going to put it into here, B16. I'm going to put it flush. You see that? B16. And then, come on. All right. Then I'm going to first heat up the board where the board and the wire touch. Okay, so three things are touching: the soldering iron, the board, and the wire. Then I'm going to touch that area, the joint, where the three of them connect with solder. Okay, and that's it. You have to be quick. In fact, I put a little too much. Yeah, I put a little too much. You see, it doesn't really sit cleanly like a Hershey Kiss. Let me suck some of it out with the solder sucker. So I'm just going to melt it again. Okay, I suck some of it out. And now, if you look, I suck a little too much, which is fine. I'm just going to put more because, you see, I'm missing some portion around it. So I'm just going to put a little bit more solder on. Don't apply too much, right? You can see that other case was already considered too much. Okay, so I'm just going to put a little bit here. So put my soldering iron at the joint. Oh, actually, I don't even need to put any. All I did was what we call reflow it. So I just heat up the joint and let the solder kind of flow around it again. All right, let me just show you. This is what it looks like now. You see that joint? This is ideal. All right. I'm going to do it one more time. I'm going to do it one more time on the other one. It's very quick. Do you see the process? I'm like no more than... Really, it's like done in, the solder portion is just done in 3 seconds. I'm going to first hold it for like 2 seconds. Then I'm going to drop in maybe 2 seconds. And done. Just like that. I stop. Okay, that's good. Oh, I'm missing a little back there. You see that? Okay, so I'm going to just try to reflow it. Not even put any more solder. I'm just going to reflow it, just pressing it. Okay, it's not enough. So, it's not enough, so I'm going to add a little bit more here. Even though I tell you to use the third hand, I don't really use it a lot.
I don't know how you can do it without it. Even with it,
Okay, so remember you want to touch the joint and then add solder in. You don't want to add solder on the iron and then dip it to your part. That's not right, because it doesn't mean you're gonna fuse to the board, and that's what matters.
Now, is that when you normally would clip it after you got a good solder?
Yeah, you can clip it at this point, but normally I don't do it until I have all the neighboring components on, because as you're soldering, you might melt that component, or you might like reflow that component. So I want to make sure like I'm out of that area before I clip. So I'm not going to clip right now. I'm going to put the next LED component in, and then I'm going to clip. Okay, so if you look at this slot, the slot on this LED is kind of going down to the bottom right, right? You see that? It's angling this way. You see that? Okay, so I need to also angle it this way, like this. If you recall, each of these columns are connected. So A is connected to anything on A. We have B's and C's. So the next one is I want to connect this LED. I want to connect it to the previous one on column C. So I'm going to put this cathode, let me see. I want to put the anode onto this one right here, like that. You see that? This wire is connected to this electrically. Even though mechanically we're not connected, they are connected electrically through this strip. I skipped row 15, so I'm on 16, and then I skipped, I'm going to 14, just because physically I want to fit the LEDs. I'm physically blocked by the shape and size of this LED, so I can't really put it on 15. So I'm just skipping it for now. Now I could have put this thing, instead of on C14, I could have put it on C10, C5, whatever. All the C's are still connected. I'm just keeping the LEDs close to each other. So for now, that will work. Okay, so let me solder that again. So I'm placing it flat down on the surface because I want it. Oh, I lost it again. Let me make sure I lined it right. Okay, good. I want it flush. Even that doesn't look good. Maybe I want to do it on row 13. Maybe row 13. I'm going to leave 2. Okay, that's better. Okay, row 13, you see it's flush now? And the LEDs, they're pointing in the right direction? Okay, good. Okay, I'm keeping constant pressure down, that way it's flush. I'm going to heat up the tri-point, so soldering iron, wire, and board. I'm going to feed solder into that portion, that area. Let it reflow. Done, like that. Let's do it again, right here. And touch this solder. 1, 2, 3. Okay, done. You see? I mean, I'm missing a little bit back there, so I could put a little bit more solder in. Yeah, I could put a little more solder in. Let me just do that. Just for sake of completion.
So you put the anode first and then the cathode, and then you're gonna do the anode again, right? In that same,
Yeah, so let me see.
I wanna make sure I'm understanding.
Okay, so I have them in the right direction. I don't know which one is which. Yeah, they're in the same direction.
They're in the same column. So it goes anode, cathode, anode.
I don't know which one's the anode and cathode right now based off this. Okay,
So this is the anode, because
So
it's
the
the
thi-
longer one.
the thinner one is the anode.
Yeah.
Yeah, the thinner one's the anode. Okay, good. Thinner one's the anode. So, what did I do? I did I did cathode on column B, anode on column C of the first LED. Then second LED, I connected the anode or the cathode to that anode of the previous one. Okay, so just like I was saying with the batteries in a remote control, you do the plus to the minus of the previous battery. You just keep doing it like that. It doesn't really matter. If you do it the opposite way, later when you hook it up to this power supply, you just have to flip the positive and negative. The main thing is to keep it consistent. If you're going to go one way, it has to go one way. Now, if you look here, I actually didn't do a great job soldering this LED because it's not flush. So, oh, I'm sorry. If you look here, I didn't do a great job soldering this LED because look, it's not flush. So I'm going to fix that. I'm just going to, so it's this side that didn't do well. So I'm just going to supply pressure on the back while I reflow that. So I'm going to heat it up. Okay, and done. You see, I pushed it back in. Still not that great. Let me just reflow it a little bit more. Oh great, now I have a little pocket. You see, there's a lot of defects that could happen. You see I have a little pocket right here now? Alright. Let me just, some of it has collected on the, some of the solder has collected on my soldering iron, so I'm just going to reintroduce a little bit more. Okay. Alright, now my LED is flush. Yes, now we are good. Now let me show you, okay, because you're going to have to bridge at some point. Really, if we want to bridge, if it's a neighboring, you could just kind of pull it together, but if it's more, if you're going to skip a hole, you should kind of put another like wire in there. So let's say, for example, we want to connect, I'm going to do row, because these ones are kind of screwed up. I'm going to go Q to S. You see Q to S? So Q to S, let me grab a wire. Does anyone have a wire stripper? Do you have oh, that's a cutter. Okay, yeah, can I grab that? Alright, let me just go from Q to S. So first, I'm going to take this wire. This is like, I'm going to start with the lower number because you can always work your way down. Okay, so 22 gauge does it. Alright, let me start there. I'm actually not going to snip the wire yet. I'm going to keep the whole thing there. It's just easier to work with. Okay, this is the side where the component's going to be, and then this is the side where all the solder. That's another thing. You want to stay consistent. So I'm just going to go Q, let me go like Q3 right now. Q3 is right here. I know it's hard to see, but once I start soldering, you'll see which one I'm working with. Q3. Q3. Alright, dang. I really need a third hand, huh? Okay, it's okay. I got it. Sorry, it's like barely on the screen. Here, let me move it up. Come on. Uh-oh. Okay, yeah. I bridged the neighboring pad for a moment, which is not good. Okay, there you go. Okay, there's a gap in between. I was concerned that between P and Q, there was not. But you can always check with the continuity meter, or I'm going to just like have a clean soldering iron, and I'm just going to kind of wipe it off. To a certain extent, you can wipe it off. Okay, you see, there's the wire. I don't like how there's a little gap here. You see right here? Anytime you have exposed wires, it's an opportunity for short. So I'm actually going to just solder that some more while I push it on the back end. Okay, I just pushed it on the back end, but now bridge that. Uh-oh, I bridged it. Oh my goodness. No, I don't want to bridge it. Okay. Alright, that was no better. Now I'm left with a little hole though. Now I'm left with a little hole. Let me put a little more solder on. Okay, good. Alright, that's what I just did. Okay. Yeah, there's still a little gap. I think I'm being too picky. Okay, now I'm gonna trim it. I'm gonna trim it. I'm just gonna trim it this much because I'm going to a neighboring area. I'm gonna go to oh my goodness, I just stripped the entire sheet off. Okay. I'll just slide it right back on. Okay. Let me go to, I'm going to go to T. I'm going to go to T here. Or I can go to, what am I going to? Okay, I'm going to S. I'm going to S3. Alright, S3, I'm going to solder it. Now this is the case where you are trying to do more than, if you're trying to move more than 2 away. Or move more than 1 away, I'm sorry. So I'm going here. And once again, I just kind of feed it in. It's easier to give it's easier to give more than to take it away. So just feed it in as needed. I have a little hole right here. You see that? Let me just flow it a little better. Okay. There's still a little hole. I might need to put more solder in. Okay, there you go. Alright. I was just trying to work with what I got. There it is. It's good now. Okay. You get the idea? Alright, so go ahead. Any questions? Let me show one more thing here. When you come up to use this multimeter, or this not multimeter, this power bank, these are exposed. You see? These wires are exposed. If they touch, they're going to spark. So make sure that, one, before you turn it on, that you are not crossing them over. Now I'm going to turn it on. Okay, and then our voltage that we want to use, you start low. Start low. This is the voltage knob, the very top one. And then you can incrementally increase it, okay? All right. When you're done, turn it to 0 and then turn it off right here. All right. But yeah, make sure these don't crisscross. So what I would do is just, to prevent crisscross, just put it straight on your circuit first. And then you can turn it on. Or maybe turn it on first, because in case the previous person didn't turn to 0. Turn it on first, make sure it's 0. Then clip it onto your 2 leads, and then slowly, incrementally increase it. Alrighty. So our boards should look clean, like kind of what I did here. Once you show it to me, like when you come up to do this thing, then we can snip it. And then it'll look nice and beautiful, just like you see right here. Something like that. All right. We have some resistors here if you're ready to do your parallel. And then for series, to be honest, we have more variability here. We could use something other than 120, because we would just have to up the voltage, right? We have something that can change the voltage here. So this is actually, if we have a different resistor, I'll just change the voltage accordingly. But try to keep it within something 100 though. So if it's like 300, that's fine, 400, whatever. Don't do like a 10,000. That would be a little bit too much.
So we're starting over, do we use
Yes.
the green PCBs?
I know, we don't have the green ones.
We don't have the green ones.
There
And my
should
other
be-
one's all messed up.
Is there no more? There's no more left?
There's a bunch of stuff on there.
You can also remove those components if you want. If you want to like make room in it. So to remove, yeah, you can take that back now.
Okay.
Oh yeah, let me turn everything off. Go ahead. We only have one solder sucker, unfortunately. There's also, oh wait, this is his personal one, so never mind. Yes, we can take this. Go ahead.
I think this is somebody else's.
Yeah. I'm gonna try to. Oh, you have a crimper?
No, yeah, I'm making connector.
That's good. Yeah. You actually have. You have this thing. Okay. Oh, nice. Okay. I might actually. Oh, nice. Okay. So, do you want to share what you're doing? You're doing some in parallel or some in series? Mostly in series.
3S3P.
3S3P. Okay.
Yeah.
That's good. Actually, that will get into our battery lecture, which is something I was supposed to talk about today. Oh, we can still talk about today. Okay, yeah. So, if you want, you can use one of the soldering irons, the one I have up here. Feel free.
Say we don't need the 120 for the,
Try to find the 120, but if not, it's not a big deal because, as you can see, everything is series. I could just change the voltage because I have this box here that has variable voltage. This one's a little harder, so we want to stick to the 340, which I've laid out here. So don't touch these ones. These ones are 340. Oh wait, I put it out somewhere. I should have like isolated it better. 340 is, oh shoot, I don't know where it went now. Darn. Oh, here's something else I'd like to show while let me show you this one too. This is good to know. This is called a breadboard. If you look here, instead of going through the whole effort of soldering, if you just want to prototype something without soldering, you can use what's called a breadboard. So if I demonstrate here, these, just like your circuit board, are connected. So they're connected downwards. So anything, they don't list every number, but we have 0, and then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so anything here, A5 through E5 are all connected. Let's just verify with the multimeter. I'm gonna borrow yours. Okay, we can verify that they are indeed connected. Okay, if you recall here, we're going to put it to this combo, and we're going to go touch function until it goes to the little audible signal. Then you can touch the leads, make sure it makes a noise. Okay, now these are too big to fit into there, so I'm just going to put a wire in here in 5A, put a wire in 5E. That way I can bring it out. Okay, and then I'm going to touch. It beeps. That's because everything's connected. Now if I go to the next one, 6E and 5A, they're not going to make a noise. Okay, so these also connect vertically. You see there's a break right here. It's physically a break. So this next one, which is 5F, G, H, I, J, those are connected to each other. These are connected, but they're not connected to each other. All right. Then we have a channel down here that runs horizontally. So that's good as a power bar. So this is a plus and minus. So everything right here, well, no, not everything. I'm sorry. So these 5 are connected. Let me see. Yep. These 5 are connected, but I don't think this is connected. Let's see. I don't know. This is how you verify. Oh, they are connected. Okay. So even though there's a break right here, well, now let me just double check here. I'm pretty sure these aren't connected. But now I'm not exactly sure. Okay, they're not connected. Okay. So this is actually a break, whereas these are just spaces. They're still connected underneath, okay? You see how I did this? I'm not exactly sure, but we use the multimeter to check. So let's build our simple circuit the one that has this parallel. This is what yours is going to look like on the board. Or this is what yours is going to look like on the actual with soldering. Okay, I'm going to grab, all right, which one? The short one is the cathode, right? Or the anode? Short one's the anode? Okay, short, or cathode. Oh, okay. Cathode's a short one. That's going to be our negative. Okay, so I'm going to put one end of this into the negative, like this. You see that? It's the short end. The short end goes into the negative rail. Let me grab a yellow. I'm going to put the short end also in the negative, okay? And then I'm going to put my red short end also in the negative. All right, let me use these numbers for like ease of reading. So right now I have my LEDs. Okay, I have my LEDs in 15, 20, and 25. You see that? Okay. Now all of them are on this blue rail. The rest of these are all on this blue rail. Okay, this is 15, 20, and 25. What do I have again? 15 is going to be the green one. 15 is going to be green. And yellow. Yellow. And then red. Does that look right? Okay, we need our resistors now. I need to find the resistors that I set aside earlier. What is our colors for 340? It's,
330?
huh?
330.
330-ish. So I just need to know the first and the third color.
Brown.
Orange, brown.
So orange something brown. That's all I care. Okay, orange something brown. Okay, so I have an orange white brown. That should work, right? Orange white brown? What is that?
It's not a white, it's a green.
What? This is white. This one.
White?
I have a orange white brown. What is orange white brown? Orange 9. Okay, so it's 390. Close. Good enough. All right. Let's just verify because it has a gold band on it. So 390 plus or minus 5%. Okay, I'm going to turn this multimeter function to the ohm. Okay, it's just on auto. Auto is the ohm. All right, let's check the actual resistance here. Right, if you're too lazy to look at the colors. If we're too lazy to look at the colors, let's see what we get here. What do we see? What is it?
388.5.
388.5. Oh, that's pretty close to our 390. Actually, I would say it's like within plus or minus 1%. Well, that was not one particular resistor. I don't know about the rest of them. Okay, so let's use that. And actually, later we can go back in and recalculate what the voltages are. But this will be good enough. So I'm going to take this out. I'm going to put this here. And then I'm going to put this to the red rail. I'm going to cross over. All the way, reach across. Reach across. Okay, do you see what I did here? So electricity is going to flow from this red rail through the resistor. It's going to go up this, down into negative. Just like what we have right here. Let me hold it from this side. Does that help? Do you see? See the flow? Okay, let's do the same thing on the other ones. Remember, resistor doesn't have a polarity, so it doesn't matter which side you plug in. Certain devices like your power, your battery, your diodes, those capacitors. We're not going to deal with capacitors in here, but capacitors you could think of as like mini batteries in a way. They're like temporary energy storage. You'll find capacitor, for example, like in a flash unit on a camera because you need to temporarily charge this little battery, and then when you take a photo, it can let out a burst of energy. Okay, but then it needs to charge up again, so that's like a capacitor. Okay, so I just did that. Let me lay it flat so you can kind of see where things are. Okay, now I need to power my rail. So I'm going to just take out this wire right here and this wire right here. Sorry. Okay, these are the two wires I'm dealing with. You see this blue one is to blue, this gray one is to positive. What is the voltage we are dealing with here on this one? 9 volts. So before I turn it on, or before I plug it in, I'm going to first make sure my alligator leads are separated. I'm going to make it to 0. Okay, it's on 0. This black one goes to this blue. This red one goes to the gray. Okay. Now I'm going to turn up the voltage to 9 volts. Oh, it's already shining. Look at that. Isn't it amazing? It works as intended. 9 volts. So we actually don't even need to go to 9 volts. I mean, 9 volts is the full brightness. So take a look here at this thing. This thing will actually tell you, you see A for current. It's going to tell you the current of the system, which is what? 0.05 amps. 0.05 amps. And then wattage. What is wattage?
Amps times volts.
Yeah, amps times volts. So anyone care to multiply 0.05 times 9? Nine times 0.05. 0.45, right?
Yes.
Okay, look what our wattage is. We only have one digit after decimal. 0.4. Oh, that makes sense, doesn't it? Oh, that's great. Okay, so our system works. Now, this was a lot quicker to build than soldering, right? So you can use this to prototype. Great. Now you can permanently put it on a board. Because this is not good for end use because, oops, I just plugged it out, all right? This is why this is good for prototyping. And later, for permanent use, you want to solder on. Okay, I want to show you the purpose of a breadboard. Okay, continue. Just want to give a whole demonstration of all the different tools we have available. Huh? No. I will go over that perhaps in 30 minutes. Does that work? See, I just dropped something. This is why this thing is just temporary. Anyone want a prototype on this? If you need a grasp better idea of what you need to do, or you can look at what I built here. Try to understand. Yes.
Okay, so you got that one.
Okay. You did these two?
I did the two more.
Okay, not
Okay, now
bad.
the third,
Not bad.
now the third one, I'm like, when do I go back on that
No.
side, or do I wanna go this way?
No, because look. Which one are you doing? You're doing series or parallel? You're doing series, right?
Yeah.
Okay. Each one is on its it's cascaded one after another.
Okay.
So if you were to double back to the T, that's basically drawing a line from here to
Going
here.
backwards,
So we
so I need
can't
to
do
go
that.
that
So you
way.
need to continue, going outwards. Yeah. So anyways, before you do this third one though, I want you to reflow this one because you see how you
Yeah,
have
I
a
was
little
looking
hole.
at that, but it was hard to get to.
Yeah, but
when I had that
this
in.
one's pretty good. Actually, this one's great.
Okay.
Keep that one. The other one, yeah. So much better this time. Yeah. Okay.
Okay,
Okay, so I'm gonna move this one out to.
So you're going to do basically the same thing. So you did TS and then you did SR. This one's going to be RQ. Okay. All right. Anyone need a soldering iron?
Thank you.
Anyone?
Bending was what's screwing me.
Okay. Any questions? You good? Okay.
Let's continue. Thank you.
Good. This one's a little bit too much solder, and now I'm concerned that they're actually touching.
I found the resistors for it, so
You might need to remove a little with the sucker here. We're safe there, but yeah, you can see what I mean. Like it's a little too much here. And we want to be really safe. You can, is it on? That's it. Is this yours? Yeah, mark it up. Alright. Go ahead and touch it. Okay. Go ahead. There's some You want to do this one? Go ahead.
Did you do the second one right there? Is that what-
This is the second one. This is the first one from last week. I already did them, but
That's cool.
he wants it clean, but I don't have a clean thing
Okay,
to do.
so, sorry, what's your question on that?
Let me see.
Yes, you need to, okay, so you can put this in QT, and then you need to put a wire out of W, just a loose wire, and then put another out of Q. And then those will go to the power supply. Put what, the wire? Anywhere on the Q. I would just say maybe put your, because we need to use this also for the parallel, so just kind of cluster together, so maybe put your wire on W.
the ones where we have.
And then put your other one on Q. That way you have this side parallel. Because if you spread yourself too far, then you're running out of room.
So.
Yeah. All right.
You got those things?
Good. Can you do the soldering in the fashion I showed? I mean, it's electrically correct. It's electrically correct.
willing.
But can you do the soldering in the fashion, especially since you didn't cut it? So, yeah. But this is good. You know it works. All right.
So,
So you would basically have to desolder first.
oh lordy.
Actually, you wouldn't even have to desolder that much. You just have to desolder this big cluster, straighten out all the individual joints, and then you're doing parallel, right?
Yeah.
So really, you need 2 more resistors. You need 3. You'll work out this way. So desolder this joint and this joint, straighten it up, then put a resistor here, here, here.
Or just 3 more? 4
Well,
altogether?
yeah. So you had it the first time I
Yeah,
did it,
okay,
which,
okay,
so
yeah.
so I get where you're coming from.
Yeah.
But like we want to do it this way,
Gotcha.
which is 3.
Gotcha.
Just like I have on that breadboard. If you want to look at the breadboard.
Did we find resistors
Well-
that are compatible or not yet?
Here's 2. We got to get a 3rd one. Let me
Okay.
yeah, search around. Let's see if you can use a color sequence. see if you can find one that's around 300 something. Ideally, so that's going to be a orange something brown. Orange something brown is your target. Or worst case, something something brown. But yeah, orange something brown is more ideal. This one still has like a little hole, you see that? Yeah, you might have to look around because I didn't really. I found some and then I don't know where they went.
Here's a 390.
390?
And
Oh, those are good. Yeah, this is usable. Okay, here. Just grab two and then we'll leave it here at the front of the classroom. We need three. He already had it. Here we go. Oh, here's a whole like random bunch that we can. I don't know, maybe some of these are real. I would just say keep the same resistors, all three resistors. Don't try to mix and match.
Still could use all the same color of these, right?
Yeah, I was just getting fancy with the red line, red, yellow, and green. Yeah, you can use the same color.
Yeah.
Right. Oh, now that I have internet, we'll go back and get some.
Oh, yeah. Not mine.
Terrence, John, John Drake. Yep. All the Johns are here. Michael. All right, Luke. Eh? Luke. Evelyn. Kyle. Kyle. David. Okay. I'm still learning names, sorry. Christian Lopez. Alright. Murdad. Chris. John again. Beth. Jennifer. Luke and Kyle? Okay. Alright. Pull up the quiz. No.
Oh, okay.
Sorry if my announcements are a little off, or like the introductions are a little off because like I've kind of been changing it.
Well, one thing is, I think I told you, like, the week 7 and 8, I'm traveling
Oh.
to Japan, so you're probably gonna have it when I'm in Japan.
7 and 8.
Which is,
Um,
so I was like, oh, we'll have the exam before, that's good, but I'm like, I don't think we feel like we're ready for
I
the
need
exam.
to like. I mean, there's a final exam, but 7 and 8. So we are in week 5 right now.
Yeah, so
Oh, you can't see the board though. Okay. That is going to be our thing, and it's fully threaded. That's our general concept, right? Actual aspect ratio and size is going to change. Okay, we have that general idea. Let's go here. So the idea was, I think everyone kind of got it, right? When I say I want the part number, it's right here. It's in the URL. You literally just copy the last portion. So you see, this is the part for this. It also says it right here. There's the part number, but it says it in the URL. So this is, for example, a washer. Okay, but we don't need a washer. We're going to go up. First thing we're going to see is screws and bolts. Let's go to screw and bolt. All right. Here on the left side, we're going to go down the list. We're going to go metric, M2, right? M2. What's our length? 8. Socket. I didn't specify, but I think it should be standard. It just says socket head. Okay, let's see. If we don't specify, it's okay. We'll see what falls out. We wanted black oxide alloy steel. Black oxide, fully threaded is our only option, so I don't even need to click on that. Some of these aren't specified. That's okay. Let's see. Okay, that's basically it. Let's see what we got here. I only see one under black oxide. There's actually another one. There's a low profile socket head screw. So there's actually 2. But let me see if there's any more specifics about this. Threading, 0.4 millimeters. Okay, 0.4. So we have 0.4 in both cases. Everything, okay, so, but this one's fully threaded. Okay, did anyone put this one? Because technically this will be okay too. Did anyone put this one down here? I didn't intend it to be this one. I intended it to be this.
I did put that bottom one.
You put the bottom one? Okay. So that technically would be okay because I didn't specify it's a normal or low profile head socket. But yeah, but this is what I intended. All right, I intended for this one, okay? So you can see here, if we go to the product detail, that kind of looks like what I drew here, right? Okay. And look, they even give you a general idea in case, like, you know, you're not able to conceptualize 8 millimeters. Okay, it's this-ish length. Okay, so then you would go here and you would copy this. And I didn't make it case sensitive because even here, if you had a lowercase a, it would still work. So that's why I didn't really, like, I accepted both. If it's, okay, so any questions on that one? All right, next one, we have similar. I'm going to draw it on here, that way people can see it. Okay, so this time we have what? We have another screw, because I said screw, okay? We have button head and torque screw, 6 millimeter long and M3. Okay, let me bring that up. So this is a button head, M3, right? M3, 6 millimeter, and what did I say? Torques. Okay, so it's gonna look something like this. Is it fully threaded? Yeah, fully threaded. Okay, actually, I heard another good approach. You could try this, which is just copy these criteria and place it in. It's not really going to necessarily yield exactly. It'll get you close. So let me see. I'm going to remove some words because sometimes you have too much words. It's actually going to confuse it.
Timer's counting down all while you're doing this.
What's that?
Yeah, 20 minutes is like way too long. Way
Yeah.
too long.
No, wait.
So the idea was, you see how quick it was if you use the proper filtering, but right here, okay, if I just search the words, it gets you there-ish, but look, it doesn't account for everything. Even though I said socket head, it gave me a button head. So, is the time enough, 20 minutes? I thought it was enough, but I don't know. I'm the one making this, so.
I think it was
Just about right?
the limit, yeah. It was-
Okay.
it was-
I was gonna say it shouldn't take you like more than 5 minutes per page, and then that still gives you a buffer.
I didn't know how little this was gonna be, so I'm running around my house looking for my magnifying glass.
Oh.
So I can see it, and by then it's like 15 minutes, and I'm like, oh,
Did you try the second attempt though? Because you get 2 attempts.
No, I did the second.
Oh, okay.
The first attempt, I got 0.
Oh,
I ran out of time. I couldn't see.
you don't need a ruler though for this thing, right? You just.
No,
You,
magnifying glass, you couldn't see the
oh, you couldn't see the screen. I thought.
Look how little that is. That's like what, 4, 5?
So okay, let me show you. On the keyboard, I press Control plus. You can do this. Control plus. It's
I
going
didn't
to.
know you could do that.
Okay, so that's a good computer hack for the future for any web page, actually. Yeah, sorry. I'm just used to seeing the little things. I didn't think about that. Yeah, so.
Yeah, it's fun being 20 years old.
But yes, hope that helps. The Control plus, and then if you want to back out, Control minus, and then you can press Control 0. Control 0 brings it back to 100%.
No, I just called him and I said, what are the answers? And he gave me the 3 answers.
Okay, well, sure.
Was that bad to say? Oh, I'm sorry.
I mean,
And here's your $20.
I got 100% if I did that.
yeah.
I did.
Okay, so let's go through here. Remember, we're going to look for something that looks like this. All right. So I'm going to reset everything. Okay, let me zoom in so it's a little bigger. Okay, can we read it? Okay, clear all. Clear all. Okay, we're going to start again. Metric. It's an M3 this time. It is a 6mm long. It is a button head, which they're going to call rounded here.
Oh, see, I didn't know that was that.
So I guess you see, even though they call it button head here, they call it rounded there. It's just, you might have to recognize some of the shapes. You can always look it up, right? There is Google. You just look it up if you're not sure. In fact, you could probably, I wonder if you just copy all this. Look, it gives you a general idea right there. Look, this one basically took all my words and it gave you exactly what you need. 6mm M3 button head. So, okay. What else do we need? M3 6mm Torx screw. Okay, we want Torx, not Torx Plus, not tamper resistant. Okay, just Torx. What else did I say? 18-8 stainless steel. Okay, I just say stainless steel, so let me just click. Okay, there it is. All right, it's the first one, but let me see. This one's not 18-8. This is A286. This is a pan head, so this wouldn't work either. We want a button head, steel button head. All right, then you take this, and once again, here's our product number. All right, that one makes sense? All right, next one, I'm going to reset again. Clear all. Let's see what we're going to imagine here. It's going to be a similar bolt because, look, it's also an M3. It's also 6mm. But this time we have a pan head and a spanner.
What's a spanner?
Oh, let's look that up. So pan head screw
Triple A. Geez.
looks like this. Pan head screw looks like this. It's like slightly rounded. It's like a button. Think of like a button on your shirt, like a flattened but still a little curved at the top.
So it's a Phillips?
No, it's the shape of the head.
Oh.
That's the pan head. The drive is a spanner, which is just 2 holes. Okay, that's what a spanner. Let me see, spanner bolt head. Let me look that up just so you. Okay, this is a spanner. There's just 2 holes. Okay, so that's,
Never seen one of those.
yeah, they're not too common, but
Elevator panels have them.
yeah, I think they're generally for tamper resistance, like because people don't have a spanner tool lying around normally. So that's why people like, that's why you might see something like that. Okay, so that's the spanner. Even if you didn't know it's a spanner, it's okay because you can go here. You can go M3, 6 millimeters. We wanted, what do we want for our fastener head? Oh, it's gonna be rounded. Okay, so I think what McMaster does here is they kind of group it together. They did both button head and pan head in rounded. If you didn't know that, you could leave it blank. Let me see. Did they? I don't see spanner actually. Ah, okay. Okay, well I found pan here. So I found pan. Let me see. What did I say here? M3 6 millimeter fully threaded.
I had to go into tamper resistance in order to find it.
You did, okay. Actually, I'm not even finding it right here. How did I find it the first time? All right. I mean, fair.
Now imagine there's a clock ticking.
Fair. I can give people that one because I don't even know where what.
In Spanner, they have drilled spanner screws and go from there.
Yeah, spanner bolt.
Scroll down.
Huh? It's in here.
Scroll, no. Swing out to spanner bolt, yeah.
Spanner bolt.
Spanner screw, yeah. Right there. Drilled spanner, stainless steel. And then just go through there and look.
Okay, let me just start up here. Metric M3. We're looking for the last one.
Stainless steel pan.
Okay, this is the one. This is the one I was looking for. This is the one. This is the one. I think what happened is we have to back out. Okay, it may not be under this one.
In the search box, you can find it.
Yeah, the one you just had up there was it.
Yeah, it is, but I don't think you can get it through here. It should. You may not.
Sounds like a trick question.
Let me see. Let me check one more time. If I go under screws, I go into metric, M3, 6. I'm gonna leave the fastener head blank. Okay, I do see a spanner. Wait,
Wait, where was spanner?
right here, drilled spanner.
Oh.
Wait a sec. M3, 6. Okay, what if I press rounded?
Wait a second.
Oh, if I, okay, it's still here actually. It's still here. I get to the same thing.
627.
I don't know what happened. Okay, you know what? I'm gonna back out. Let me see what I did the first time. Because, like, how come we couldn't find it that time? Let me back out. Because I basically found this by just clearing it and then I just chose random things. And I'm like, okay, I got to this thing. Okay, this is where we were, right? And there's no spanner. Yeah, there's no spanner. So let me clear the 6 millimeter. Let me clear the M3. Is there anything else? There might be something still clicked on. Pan, let me clear that. Okay, so basically the only thing I have right now should just be the metric, right? So then if I go back, M3, 6, there's no spanner. What else do we have selected? Yeah, it's possible. That's weird. This time around, I don't.
Yeah, that's right. That's what I got the first time I did it.
Okay, that's okay. I could give that to y'all. That's weird. That is so weird. Okay, I'll give the points to everyone for that one. But just as a practical exercise, let's say you wanted to find a spanner. You wouldn't just be like, oh, I'm done. Like, you still need to find that part, right? So you could just go into the search box, right? We saw it the other way. But I didn't show that last time, so I give that to you.
I think that's what I did. I put spanner up there.
Yeah.
Spanner M3, and it gave me.
Sir, let's do it. Spanner M3 6 millimeter. Well, let's give you the tools. So if we look up bolt,
Screw.
you could say screw. Okay, yeah.
See,
So-
that's
So actually, yeah, we literally got to the same thing. So,
620.
but I'll still give it to you anyways because like that one somehow there's a bug as we just saw in their filtering that I don't know why. It showed up for me when I was making the quiz, but that one. Okay. Do you all understand how we can find things? And this is just bolts. Like John has something he wants help with, like a bearing. I need to look up a bearing. They have all different types of bearings, so I need to find out exactly what you need, and all different specifications. So I still have to think about what would be best for you, actually. But yeah, if we just look at the traditional ball bearings, there's different sizes. What's your shaft diameter? What's your outer diameter? What's the width? The bearing type. If you want flange, bearing trade number. Actually, I have no idea what this means. Let's see what that says. You can always click on the eye. Oh yeah, go eat if you want to go eat. We'll meet back at 6, a little shorter. But you can always, we'll just do more, okay, fine. We'll just do more soldering anyways. So if you need a little more time to eat, it's okay. I do want to like go over a couple slides though, because we kind of flipped the order. I'm glad we did more soldering today, but I want to show more stuff because I'm trying to show you guys how to build your own drone, right? Like, yeah, that was like one of the requests. So I need to go over some more concepts. This type of board, the one that are not connected, then sometimes you're going to have to bridge it eventually at certain points. So if you look here, we have a diode, and then we have a resistor. They're separated by 2 holes. So there's a couple ways you could do it. You could either try to pool a bunch of solder, but it's going to flow around, so it's a little difficult. You can also introduce another wire to jump from one to the next. Or what I'm going to do here is I'm going to kind of use this end piece as a wire. Okay, I'm going to bridge it across. So what I'm going to do is first I'm going to snip this one, all right? You see this one? So do you have the
Snippers?
Yeah.
Yeah.
Okay.
Did you rid that circle in the middle of the screen?
What circle? I'm sorry, I can't say that. Yeah. Thank you. Okay, so again, right now we need to bridge between this LED and this resistor. There's no bridging in between these. All these are independent. Before I trim it, I'm gonna make sure this was a good solder joint. Right? You agree? That looks like a good solder joint to me. Okay,
You
so
told me that was too much material.
yours was
I know,
yours had a little bit of love on it. All right.
What about a C plus?
Yeah.
All right. I just
Like a D.
It's a bigger Hershey's Kiss.
yeah, it's a Hershey Kiss Mega. Okay, so I just trimmed it, and now I'm gonna lay it across like this. All right. This is gonna be my poor man's way to do it. Okay, now I'm going to. Can you hold this because I don't have a helping hand. No, I like a real hand, just in case. I'll hold it from this side.
You're just gonna
Okay.
solder on top of it?
Yeah, I'm gonna solder right there. Hold it down, from down, right there.
There's one of the legs over.
All right, yeah, I just brought the leg over, so I'm gonna heat up this joint right here.
Ow.
All right.
Can you solder that guy's finger?
Can I solder it to his mouth?
Y'all can do whatever you want. All right, yeah.
When you're done, I got this cavity you can fill in.
Oh. Hot solder.
It is lead after all.
It's really soft lead though.
It's only 7,000
I was
degrees,
trying to do that
700 degrees.
Feel a mild
Right.
burning
Yeah.
sensation.
Okay,
That's why
you
I
see?
got so clumped up.
Okay, I just did that. Good. Thank you very much. And now I'm gonna trim this. Don't trim until you show it to me, just in case you need to make adjustment. All right, there you go. Now this LED is connected to this solder or to this resistor. Okay. All right. Good. Now there is a risk to doing this thing, is that if you ever put this against like a metal surface, it's gonna short it out. Because you see, actually in fact, even if you didn't do a bridging like this, if you put this thing, this bare circuit board against any metal surface, you're gonna short things out. So you should have some form of like buffer in between, yeah. That could be as simple as just like a little plastic sheet or something like that, yeah. Okay, so you could do the rest here. You could just bend this over. Let me check the rest of your resistors look good. So you can trim one. You could trim that. You could bend it over, solder, clip the end. Okay?
Thank you.
You're welcome. Now that's if you have this. If you're lucky enough, you don't have to do that thing because you already have the bridges. Okay.
Do it all again.
Yeah. When you're measuring voltage, you can and resistance, you can just measure across two components. When you are doing current, you need to be in line. Think of it as a meter, just like a gas meter, electric meter. You have to like be part of the system so it can count like how much has flowed past it. Okay? So you actually need to break open the system and you need to be in it for that to work. So you can see that there's actually 3 ports down here. This COM is always going to be the black. This, when you want to do current, that's when you need to switch here. Everything else you see voltage, resistance, frequency. You can do milliamp, so like little voltage. But if I turn this back on again, look at my system here and tell me how many amps we have. How many amps are we using? It's actually really little. So technically we could probably stay here. Like this will take a current, this will handle a very low current. But reality is you want to unplug this one, you want to put it into this side. Okay? Now this is used for measuring current. So all of these over here need to be using this side. Okay? And then for you to measure current, you need to break the system. So you see I just broke the system. I put one lead here and I put the other lead here. Okay, I complete the circuit. You can see I complete the circuit because the lights turn on. You see the lights turn on? So I'm part of the circuit now. And then when you're part of the circuit, you can read the current. What is it? 0.003. What do we see here? 0.004. It's basically more or less the same. Yeah, it's within the factor of tolerance of our devices. Okay, so that's how you read current. You have to be one in the device. Now, because we're soldered, there's no way for me to like easily break another thing. But if I was to break another component and measure the current, it should be 0.003, 0.004, right? Because current is the same throughout. But these are all soldered on, so it's kind of hard for me to do that. If I had the breadboard, I could do that easily. Take out things and then measure anywhere along the point, and it'll all be the same current. All right, so there's that. I'm going to take this. I'm going to switch it back to here. Now I'm going to look at our parallel circuit. If you look at the parallel circuit, this was done good. This was done correctly because all the components on this side. It's also flat. That's a good sign. They're all flat. And the LEDs are all facing slanted. The slot is to the top right corner. Okay, let's look at here. So we have this board that needs to be connected. So we have a common rail right here. So these all are connected, good. And then we have our LEDs that are connected to the resistor. So these are each of our 3 LEDs, 1, 2, 3, and then there's a resistor that goes across here. This is a common rail. Basically what you see here. So this is like visually the same exact thing that you see here. You see? Just like that. Okay, so let's hook it up. I'm going to turn down this voltage before we plug it in. Okay, I'm going to turn up the voltage. And there we go. I'm actually don't even need to turn it up that high. I'm just going to turn it up to 3 volts. Okay, so what do we remember from parallel circuits? What's the voltage across each device? Huh?
2.2 volts.
2.2.
Right there.
Yeah, that's ideal. Yeah, exactly. It should be 2.2, but the voltages across each of these. Okay, well, I wanted this to be a higher number. Let me throw this up to a higher number. Okay, I'm just going to throw it to 5 volts, even though it's kind of really bright now. I don't want to burn out the LEDs. But it's still going to be, it should limit out to 2.2. That's not a great example because I wanted to show like how voltages are summations, and then current is, and then like in parallel voltages are the same. But anyways, it's the same if I was to press this. Wait a sec. Oh, I'm on AC. Okay, that's a common mistake too. You have to make sure you're on the one with the line, not the squiggly line. The squiggly line is AC, alternating current. We're on DC. Okay, 1.6. So we're basically getting the same thing as last time. Yeah. But they're going to be the same throughout because in parallel we have same voltages across each individual component. There it is. Well, it's 1.9 on that one. It's basically 2 volts. Okay. Interesting. Whoa. Did you use different? Oh, you use different resistors. No wonder. I was like, that's right. We were talking about this. I was like, why are they not the same voltages? Okay, he used different resistors. That's why like these are not the same. Okay, so this may not be the best example. We see right here, those two are the same, and then this one's not. But okay. Just wanted to show you, I guess, from a practical standpoint. Any questions? I hope the repetition of the examples help. Okay. All right. As conclusion, current is the movement of electrons from atom to atom. Okay. So, as you saw here, in order to measure current, you need to be in the loop. You have to be part of the circuit. Okay. Voltage, on the other hand, is the potential. It's like the pressure difference. So you can measure pressure in a pipe even if the spigot's not on, right? You can measure pressure. Or when the spigot's on, you can still measure the pressure, right? So that's basically, you can go across just to measure it. It doesn't have to be a live circuit. But if your circuit, the switch is open, there's zero current, right? There's no flow. But there's still potential. Just like our batteries sitting right here, the 9-volt batteries, there's still 9-volt battery, but there's no flow. There's no current right now. So voltage will exist even in an open circuit. So think about that. So that means you can measure across, right? If something's broken, you can still measure across, you can still measure the circuit. Whereas this current, you have to be in it. And then insulators inhibit the flow. As you've seen here, these are insulators in a way. These are resistors. But we have insulator. This board, this fiberglass board, is an insulator. So that's why we have to bridge across in order to get them to connect. Because on their own, the electrons aren't going to flow. Okay, you can build, the power is, okay, so Ohm's law, V equals IR. Current, voltage, resistance are related through V equals IR. And then power is watts, which is voltage times amps. P equals IV. Energy is power over time. So now that's watt hours. Later, when we look at the batteries, we'll see that. Okay. And then electrical circuit, like we have here, has a switch, load, power supply, and conductor. That's like a very basic terms. We actually don't have a switch on this. The switch is just you plugging it, unplugging it. But you can imagine it's a switch instead of you plugging, unplugging. We have our load. The load is going to be any component you have on here. So the LEDs, the resistor, those are your loads. Then we have our power supply, this thing. And then we have the conductors, which is really your wires and your solder. In this case, the solder like river is kind of like your conductor. Okay, it's connecting all of those devices together. You can arrange your circuits in series and parallel, or series parallel. If you look here, this is actually this is a series parallel, right? These are parallel, but this thing is a series. So really, like, trying to think, yeah, unless you didn't have the resistor, then everything would be purely parallel. But because we have these, this is considered like this would be considered like a series. All right. So you see the series within the parallel, yeah. Okay. And then remember your prefixes. Milli is 1,000th, 1/1,000, and kilo is 1,000. So you're gonna see that a lot. You see it on the meters. Make sure when you do the calculation, you count for that. So previously, remember we were doing the calculation, we're dealing with milliamps, and I converted it to amps. That way, when we're doing Ohm's law, V equals IR, we're not going to get confused with the scale of the numbers. So I just want to put everything in the same. If you're going to, yeah, it makes things easier. Again, you can work with mixed scales, like killi and milli, but you really got to be diligent in keeping track of everything. I suggest you put them all in one type. If you're going to deal with all millis, then stay with all millis. If you're going to deal with kilos, stay with all kilos, or just the baseline unit. All right. Okay, let me see. Okay, we have a little bit of time. I'm going to get started with batteries because all of this electricity stuff I want to go over so we can start talking about batteries. Okay. Now that we understand parallel and series, this will make sense, and also some basic electricity, this will make a little bit more sense. So, anyone do FPV? Okay, so you have to charge your batteries, right? Do you understand all the numbers you punch in when you charge your batteries? Or are you using a DJI FPV? Okay, so DJI makes things way too simple. Like you take this battery, plug it in, done. Okay, if you're doing FPV, like you are just going to get a battery. I don't have it out here. Let me pull out a kit. When you end up doing FPV, so these are the kits that we're going to build. Okay, when you end up doing with FPV, you're going to get a battery like this. And they come in different shapes and sizes. And then you're going to need to plug it into a charger that has a screen, and you have to punch in a bunch of info. So it's not as simple as what you see with DJI. They make their charger specific to their battery. So easy, but it's not very versatile with other stuff. You can get a generic battery. We have one in the back. But you can take any LiPo battery like this. Look at some of the numbers you see on here. What do you see?
14.8 volts, 22.2 watt hours.
Watt hours. What is that, by the way? What's watt hours?
Energy.
Energy. Okay. All right. What else do we have number-wise? I know it's kind of hard to see.
1500 milliamps.
1500 milliamp hour.
100 C4S.
100 C4S. Does anyone know what any of those? We kind of know at least two of them, right? We talked about.
4 cells.
Oh, where'd you get that from?
4S.
Okay, good. So you might think, what is S have to do with cells? Why is 4S? Does anyone know? Does anyone know why it's 4S?
Not 4C.
Yeah, C is actually already taken right here. And I'll go into the details about what that means. But why is it called 4S? You are right, it is 4 cells. Why 4S? Hint, it has something to do with what I have behind me. It's in series, correct. So they have 4 batteries in series. So, let me ask you this. Okay, I'm going to draw this thing. We have 4 batteries in series. I'm just gonna simplify this and draw it like this, alright? Just imagine like a bunch of AA batteries. This is series, correct? Is this series? Okay, I'm gonna read it to you. It says 14.8 volts. You know it's 4 cells in series. So, knowing what we know about series circuits, what does that mean each cell is?
1/4 of 14.4.
Okay, yes. So 14.8 volts divided by 4 cells is what?
3.7.
3.7 volts per cell. You see that? I have volts per cells. So 3.7 volts per cell, right? Because we are in series. I don't really see it too often, but if you have a bigger battery pack, you might see, huh?
12S? That's what.
Well, I mean, I don't really see that either, but what I mean is you'll sometimes see P. So you see a 4S2P. Okay, so the P is going to be parallel. So you have 2 parallel packs of 4S. What is the voltage going to be on that one? Huh? What is parallel? Let me draw this again. So we have another set right here. This is now parallel. What is the voltage going to be across this point right here?
The same 14.8.
So this is a 4S2P. What is it going to be? Huh?
14.8.
That's right. But what's the difference? You still get, huh?
Because they're in parallel. You'll
Yeah.
have twice the
So
current.
why would they do something like that? Why would they? What's the difference between doing a 4S like this, just this, and then having a 4S 2P like that? Why would you do one over the other?
More energy.
More energy in the sense it's more capacity, right? It's like you have 2 sets of batteries. It's like having 2 tanks now, two tanks in your car. Okay, so you still have the same voltage, but now you have double the capacity. Okay, so that's why you'll see that usually on bigger batteries. You'll see a parallel circuit.
This is 12S20C, 44.4 volts, 710.
Okay, let's take a look at that. Is this your
This is
drum?
the, yeah, this is the. unit.
Okay, so it's a 12S what?
20C,
20C,
44.4 volts,
0.4 volts. Okay,
710.4 watt hours,
7 what?
710.4, 710.4,
Uh huh.
and then.
Watt hours?
Yeah, and then 1600 milliamp hours.
1600 milliamp hours. Seems kind of low. 1600 or 16,000?
Sorry, 16,000.
Okay. I was like, this is a 1500 milliamp hour battery.
Okay,
I was like,
16,000, sorry.
okay. Even that seems a little low, to be honest. But let's take a look at this. So
It's running off of 2 though.
it's running off of 2. Okay, so then that would be what? You would just
Double
you would just
everything,
no, you wouldn't double everything.
Just the.
Okay, just the capacity.
Okay.
Yeah. Well, it depends on how it's wired, but more than likely, just like the Inspire. Anyone fly the Inspire? The double battery?
Yeah.
Okay, do you know, think about this. Why are you able to hot swap batteries? Meaning you can take one out, the thing is still running, and then put another one in.
It's still powered.
It's still
Take one
powered,
battery.
but what happens when you take one battery out? What happens to the system?
It knows it's got a problem.
It's not necessarily a problem, you just change the system. But look back up here. You basically, when you take out one battery, you X one. So what's happened?
It goes twice the
Less
current,
power.
but you have the same voltage.
You have the same voltage, so the system still stays on, but your capacity is cut in half. Which doesn't really matter when the drone's just sitting on the ground in like an idle mode, right? So that's how you can hot swap it, because you're still powering with the same voltage, but of course you cut your capacity by twice, but it's not like you're draining the thing like at the same rate that you are when you're flying. So that's why it's okay. Hopefully that makes a little more sense, right? Like, okay, so you can hot swap it. So more than likely your drone is doing the same thing. It's just increasing capacity. So I don't know if you can hot swap, but You can hot swap. Okay, for this.
One powers it up. and-
Exactly, it's for the same reason.
I
Yeah.
actually didn't know you could do that with the Inspire either.
So the Inspire, yes, you can. You don't actually have to turn it off. You can
Okay.
take out one
I
battery,
never knew that.
put in a fresh battery, then take out the other one, put in a fresh battery. Yeah, just in case that extra minute is like, you know, life-threatening or something like that. You need to like do something. Okay, let's take a look at your drone here. So it's a 2S, no P's. No P's on this no P's on this battery, just a 2S, straight 2S or 12S. I'm sorry.
12S, yeah.
Okay, so I'm not going to draw out the individual cells. Let me just do it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Wow, that's a lot. Okay, like this. Okay, if it's 12 cells, 44.4 volts divided by 12 cells is what per cell? Huh?
Sigma 7, 3.7.
It should more or less be that, but let's just verify. Can someone do it? It should more or less be that. If we're talking
3.7.
3.7, is that a coincidence? Is that a coincidence?
That's with the voltage of a LiPo.
That's great. That is the voltage of a LiPo cell. That's at least the baseline voltage, okay? What I mean by that baseline voltage is that in reality, when you charge the thing up, it's actually going to go up to like 4.2 volts. So then when you measure it, okay, let's take a look here. So it's going to go up to like 4.2 volts, and when you use it, it's going to go down to like let's just say 3.2 for sake of simplicity. Really, you don't want to stop at 3.2. That's a little low. You want to kind of stop more like 3.3 is kind of my minimum, but yeah, 3.2 for sake of simplicity. So if that's the case, even though this thing says it's a 14.8 volt battery, when you charge up a 4S battery, you're going to get 4.2 volts per cell. You have 4 cells. What is the actual voltage going to end up being when you measure this? 16.8 volts. Now, when it's discharged, it's going to be 3.2 volts-ish, all right? I don't know. It's like you kind of want to target more like 3.3. But I'm just going to say this. Times 4 cells, what is it going to be when it's discharged? 12.8, right? Do you see that? Okay, I'm going to take a multimeter to this. Let's find out what it actually is in terms of percentage, all right? Percentage full. So this is like 100% full, and this is like, let's just say 0% full. Really, you never charge it all the way to 0. In that case, your battery is dead. This is something I want to demonstrate. It has to be next time. You see, these don't turn on. Does anyone have a DJI battery that doesn't turn on anymore? Like this. You see, I keep clicking it. Actually, there's a way to hack it. So when we have time, and when we get better at soldering, because you actually need to put this together by soldering a little bit, so then we can actually try to break this open and revive this battery. Which, you know, on the Spires, those things are like $100 each, I think, the batteries. So those are all dead. All those batteries are dead. So if you can revive it, like, that'll be great, right? What happens is this has a software built in where if you drop below like a certain voltage, it says stop. I'm never going to let you use it again. And it's for a good reason, actually. So I'm just saying, for us to revive it, you still have to be cautious because the chemistry has changed on the inside. So DJI has put the software stop to prevent any potential issues down the line. Did you have a question?
Years ago, we were taught we could jump a battery with like a paper clip or a wire in the field, and it'll reset it to charge.
Ooh, I don't know about that. On a DJI drone?
No, this was in the military.
Oh,
We were using LiPo batteries.
okay. I don't know. Yeah, I wouldn't suggest doing that for sure. I know, but they still have voltage in there.
That's right.
Yeah, so even though they're dead in terms of our usage through this onboard chip, they still have voltage in it. Just like any battery, when it's like dead, it just doesn't have enough voltage, right? You see right here, we're at 12.8 volts. That's dead. The drone can no longer fly with this, but there's still voltage. So be careful because, you know, lithium-ion batteries, they're kind of dangerous. You've probably seen like or heard like hoverboards and the Samsung Galaxy catching on fires and stuff like that? Yeah. And now actually I just heard some airlines like in Asia, they ban the use of these like portable power banks in the cabins.
Oh, really?
Yeah, because they probably had some issue where these things catch on fire. Because they are literally little bombs sitting in here. If you think about it, if you like puncture this, it just like it becomes a fireball. It's not big enough to like boom blow up the whole thing, but it create a lot of smoke. And there's like, shoo, it's like a little firework, okay? Not trying to inspire any ideas, but I'm just saying whenever you walk around with this, like in the airplane or even your laptop and stuff, with anything with a battery, like if you puncture it, yeah, exactly. Lithium is a group 1 metal, and it is very reactive. Same with sodium. If you ever look at sodium and water, lithium and water, they're very reactive. Okay, so our nominal is, what is it again? 14.8 volts. Okay, so that's like our 50%. Okay, let's see what this is. So I'm going to take this multimeter. Okay, multimeter, and okay, I'm not going to talk about this plug just yet. This is called a balance plug. So what happens is, as you know, we have multiple cells inside. You want to make sure when you're charging that they're all at the same voltage, more or less. So that's what this plug allows you to do. This is like our usage plug right here, the main plug. So let's just take a look at this. This allows me to take the entire, voltage out of this battery, and this is what you plug into your drone. So let me prop this up. Can you see? No, not too mud. All right, is this better? Good. All right. I'm going to put the black in the black in this. All right, what do we got here for voltage? 16.6. 16.6.
Close enough.
Wow, this thing is mostly what? Mostly charged. I would say it's basically like 95% charged, okay? All right. I will go more into battery care, but this is actually not a good thing to keep it fully charged. Lithium-ion batteries, they like to be kept at like a 60% storage mark, since this has been sitting here since last semester. Okay, so when I tell all my drone customers, like if you're not going to use your drone batteries for more than a week, discharge or charge it up, depending on what state you're in, to like 60-ish%, okay? This is just for the longevity of the battery. It's not like it's going to blow up or anything like I said previously. It's just that if you want your batteries to last longer, you want to target that 60%. In fact, even these Apple devices, they have now put these things in here that it will only charge up to 80% based off your habit. And it'll be like, hey, I notice that you are going to be plugged in usually at nights and overnight. So I'm only going to charge it up to 80%. Same with your phone. And I'm only going to fully charge right before you get up. Okay, it reads your patterns. And the reason it does this is that's optimized charging. Yeah, that's optimized charging because these are all lithium-ion batteries. They're trying to extend the life of your battery. It's, of course, when you need to use it, charge it up to 100%. But generally, you don't want to keep it at 100%. It's also not good to keep it like at a very low voltage because it's going to continue dropping until you get a dead battery like these ones. Okay. But yeah, I'll go more into detail about that. But you can see here, we are able to determine the percentage from something that has no apparent meter on it, right? These have meters built in, these don't. There's no way to tell except for you to take a multimeter. Or you can plug into the drone and look through the goggle, which has a built-in multimeter, right? That's the way to tell what the voltage is. A lot of times, FEV, they're not going to tell you battery percentage. They're just going to tell you voltage. You're going to have to know I'm using a 4S battery. Therefore, my range is what you see here on the screen. It's between 12.8 and 16.8. And whatever voltage you get is your in-between, is like your percentage. You kind of have to do that math. Every battery is going to be different. If you're going to do a 3S battery, what would that voltage be between 0 and 100? Okay, 3S battery. Let's take a look at that. Oops. 3 cells. Our nominal voltage is calculated at 3.7 volts per cell. Times 3 cells, what would that be?
11.1.
11.1 volts. Okay, so that's this position right here, just like what we see here. But we have 4.2 volts per cell as our fully charged. What would that be? 12.6 volts, and then if 3.2 volts times 3 cells, what would that be?
9.6.
9.6 volts. Okay, so this is our range right here, 100% to, let's just say 0% if we were to give it a percent. I don't have a 3S battery, but if you had one, you see how the numbers shift? You can't have a hard number. Oh yeah, 16.8 is 100% charged. It doesn't work. It has to depend. It depends on your battery. So for the 4S, yes. The 3S has a different limit. What doesn't matter is your capacity, because we're talking voltage. If this was double the size, because it was a 4S 2P, it's still the same voltages, right? Because we're talking parallel. Parallel voltages are the same, okay? So you would still use the same thing. So really what you look at is the number in the series. That determines your range of voltages that you deal with here. All right, so if you have a battery next time, feel free to bring it in, and then we can analyze it, because I want to go through a lot of examples of batteries so that way you can look at these numbers and you can understand what they mean. Later, we can charge them properly without blowing it up, right? That's a good thing. And then that also means you can buy your proper batteries for your drone. Knowing this information allows you, if this supplier no longer makes the batteries, it's okay. I'll just go buy another battery with the same specifications, or maybe even one slightly different. If you find one that's 1600 milliamp hours, that might still be okay. That's just bigger capacity, but you still have like the same voltage. So, all right, we'll conclude here for today. Make sure you turn everything off on your station.